Space is not empty. It only pretends to be. For most of human history, the universe was a silent movie. We watched light. We measured color. We mapped stars like pins on a black board. We learned to read reality through photons because photons were what reached us. But light is not the whole story. Light is what happens after something already happened. There is another messenger, one that does not care about dust, one that does not care about darkness, one that does not travel through space the way light does. It is the vibration of space itself. Gravitational waves are not waves inside the universe. They are waves of the universe. They are ripples in the fabric that holds everything. When they pass, they do not brighten a telescope image. They stretch distance. They squeeze time. They move the ruler you are using while you are using it. For a long time, they were a prediction that sounded like poetry and behaved like a ghost. Then, we built instruments sensitive enough to feel them. We caught the first sharp chirps from black holes colliding, brief and violent, like a hammer strike in the dark. The universe was suddenly not silent. It was singing in bursts. But those chirps were only the loudest notes, the obvious ones, the collisions close enough and heavy enough to stand out. Now comes the disturbing part. Because the universe does not only sing in bursts, it also hums. A constant low-frequency vibration all around you all the time, so slow that one wave can take years to pass, so deep you do not feel it in your bones. You feel it in the timing of distant stars. And if this hum is real, it means something enormous. It means the cosmos is filled with countless pairs of supermassive black holes orbiting each other in the cores of galaxies across billions of light years, forming a gravitational choir so large that no single voice can be isolated. You do not hear one singer. You hear the crowd. A background. A gravitational wave background is the sound of structure evolving, the sound of galaxies colliding, the sound of monsters circling, the sound of the universe building itself through mergers and violence and time. This is not a story about one black hole. This is not a story about one event. This is a story about a field of rhythm spread across the sky. And the frightening possibility is that the hum might be louder than it should be, or shaped differently than it should be, or coming from sources we did not expect. Because the moment you measure a background, you stop asking, did a black hole merge? You start asking, how many are there? How massive are they? How quickly do they form? How fast do galaxies merge? What is the real architecture of cosmic growth? The background becomes a census, a confession, a fingerprint left on spacetime. The problem is that this hum is too slow for the detectors that caught the first chirps. Those instruments listen for ripples that rise and fall in fractions of a second. They are tuned to the screams. The background is not a scream. It is a tide. To detect it, we needed an instrument the size of the galaxy. Not mirrors, not lasers. We needed clocks, not human clocks, cosmic clocks. Because if space-time is humming, it will not flash in your camera. It will do something subtler. It will make clocks drift. The universe has objects that keep time with an arrogance that feels impossible. Pulsars, the crushed cores of massive stars, neutron stars the size of a city with the mass of the sun, spinning with extraordinary stability, sweeping beams across space like lighthouses. Each rotation produces a pulse, and those pulses arrive with such regularity that some pulsars rival the best clocks we can build. They are not perfect, nothing is, but they are stable enough that tiny distortions become visible. Tiny delays, tiny advances, tiny irregularities that would mean nothing if they appeared in one place. But if the same kind of irregularity appears across the sky in many pulsars in a coordinated pattern, it stops being noise. It becomes a message. This is where the story turns unreal. We built an observatory not by launching a telescope, but by watching a network of dead stars tick. We measured their pulses over years and turned the Milky Way into a detector. The method is simple in concept and brutal in execution. If a gravitational wave passes between Earth and a pulsar, it stretches and squeezes the distance, changing the travel time of the pulse. The pulse arrives a little early or a little late relative to expectation. One pulsar doing something strange could be 1,000 things: plasma between stars, instrument drift, timing errors, a pulsar glitch, statistical weirdness. But a true background would not distort just one. It would distort the entire sky, not identically, not in lockstep, but in a specific geometric pattern that depends on the angle between pulsars. This is the key. A real background does not merely add randomness, it adds structure. If you compare timing deviations between many pulsars, you can look for the signature correlation predicted by gravity itself. It is not a vibe, it is a curve, a specific shape that either appears or it does not. For years, the data hinted at low-frequency noise that grew stronger on longer timescales, something common, something persistent, something that looked like a background. People argued because in precision astronomy you do not declare a revolution because a plot looks exciting. You declare it when alternatives run out of oxygen. Solar system modeling errors can leak into timing. Interstellar plasma can imitate delays. Telescopes and pipelines can leave fingerprints. The universe does not make it easy. It makes you earn every claim. Then the collaborations kept watching. They refined their models. They added pulsars, they tightened calibrations, they separated noise sources like surgeons separating nerves. Slowly, the picture sharpened. Multiple independent groups began to see the same kind of low-frequency signal, the same sense that the sky was not statistically quiet. The decisive question became unavoidable. Do we see the spatial correlation that gravitational waves demand? Because that correlation is the smoking gun. Not, we see extra noise, but we see the geometry of spacetime. If that correlation holds, then the universe is humming. And if the universe is humming, the source cannot be small or rare. The leading culprit is a population of supermassive black hole binaries, pairs of monsters formed when galaxies merge. The galaxies collide, their stars pass through each other, their gas shocks and ignites, and in the center, the black holes sink toward each other, become bound, tighten their orbit, and leak energy as gravitational waves. The nanohertz background is not the last seconds of a merger. It is the long spiral, the slow dance that can last millions of years, repeated across cosmic history so many times that the signals overlap into an ocean. At first, that sounds like a normal consequence of galaxy evolution, a background you expect. Then you look closer. Because once you accept a background, you inherit every question it forces. How many mergers happened and when? How massive are the black holes? How efficiently do binaries harden? Do they stall? Does gas help them shrink, or do stars dominate? Are our models of galaxy growth correct? And deeper still, are we sure the background comes from black hole binaries at all? Because when you open a new window, you do not always see what you predicted. There are other possible sources that sound like science fiction until the day the data refuses to go away. Cosmic strings, early universe phase transitions, relics from moments after the Big Bang when the vacuum itself may have changed. This is why the hum matters. Gravitational waves bypass the barriers that limit light. Dust cannot hide them. Gas cannot absorb them. They carry information from places light struggles to escape. Light tells you where something is. Gravitational waves tell you what it is doing. And a background is not one story. It is the statistical sum of billions of years of stories, a cosmic roar you can use to reconstruct the invisible game being played behind the bright images. But before any of that, the background demands one brutal standard: proof that what you hear is not an echo of your own assumptions. A pulsar timing array is an instrument made of messy components. Pulsars have quirks. Space is filled with plasma. Earth's motion must be modeled with extreme precision. Observatory clocks drift. Pipelines contain choices that can imprint patterns. So the background does not only demand wonder, it demands suspicion. It demands correlation, not excitement, not just a common signal, but the specific spatial correlation gravity predicts. If that correlation is real, the universe is humming. And the hum is not background noise. It is the sound of your model being tested. In the next part, we step inside the instrument that listens for it. We follow the logic that turns pulsars into a galaxy-sized detector. We trace the curve that decides whether this is space-time itself or something we accidentally invented. And then we confront the question no one wants to say out loud. If the hum is real, why did we not hear it sooner? To hear the hum, you have to do something that feels almost absurd. You have to treat the Milky Way like a laboratory instrument and treat time like a microscope. A pulsar is a cosmic metronome, but only after you strip away the illusion that it is simple. Every pulse you receive has traveled through a messy universe. It has crossed turbulent plasma that bends radio waves and delays them in frequency-dependent ways. It has passed near gravitational fields that slightly alter its path. It arrives at a planet that is spinning, orbiting, wobbling, and being tugged by every major mass in the solar system. And you are trying to measure arrival times so precisely that a shift smaller than a heartbeat can become evidence of a wave that takes years to pass. So the first step is not listening. The first step is subtraction. You build a timing model for each pulsar. You account for its spin rate and how that spin slowly changes. You account for orbital motion if it is in a binary system. You correct for dispersion in the interstellar medium because ionized gas delays low-frequency radio waves more than high-frequency ones, and that delay changes over time as the pulsar, Earth, and plasma clouds move. You convert your measurements to a common reference frame, the solar system barycenter, because even the motion of Jupiter can shift your clock if you are trying to be perfect. You include relativistic effects because at this level, relativity is not a philosophy, it is plumbing. Then you take the real arrival times, subtract the predicted arrival times, and you stare at what remains. Those leftovers are called timing residuals, and residuals are where reality hides. If the universe were perfectly quiet, residuals would look like random scatter, dominated by measurement noise and little imperfections. In practice, they do not. They carry patterns. They carry drifts. They carry low-frequency wander. They carry what astronomers call red noise, power that grows on longer timescales. And red noise is dangerous because the hum you want to detect is also a kind of red noise. A gravitational wave background is a low-frequency process. It is a slow tide in spacetime. It will not show up as a clean periodic signal in a single pulsar. It will show up as a common correlated wobble across many pulsars. This is the trap. Many things can create red noise in pulsar timing. A pulsar can have intrinsic spin irregularities, tiny changes in rotation that accumulate over years. The interstellar medium can vary and imitate slow drifts if you do not model it correctly. Earth-based observatories have clock errors that can appear as a common signal, because every pulsar would inherit the same timing mistake. Even the model of the solar system itself, the ephemeris that tells you where Earth is relative to the barycenter, can be slightly wrong in ways that leak into residuals and masquerade as a cosmic signal. So detection is not about seeing red noise. Detection is about proving the noise has the geometry of gravity. There is a specific pattern that a stochastic gravitational wave background must imprint on the sky. Not a pattern in one pulsar, a pattern in the correlations between pulsars. You take pairs of pulsars. You measure how similar their timing residuals are over long timescales. Then, you plot that similarity as a function of the angle between the pulsars on the sky. If the background is real, those correlations do not come out flat. They trace a very particular curve, a relationship predicted from general relativity. It does not depend on the details of your telescope. It does not depend on the personality of a single pulsar. It depends on space-time. This curve is ruthless because it is not something you can wish into existence. It has a shape. It rises at small angles. It falls. It crosses through a dip. It becomes slightly positive again at wide separations. It is counterintuitive, and that is precisely why it is powerful. Instrument errors tend to produce simpler patterns. A clock error produces the same sign everywhere. A solar system modeling error tends to imprint a different spatial signature, often resembling a dipole. Interstellar plasma effects do not produce the same angular correlation across the whole sky. The gravitational background does. This is the killer curve, the checkmate, the line that decides whether you are hearing the universe or hearing yourself. For years, researchers could say, we see a common red noise process, we see hints, we see a signal that looks like it grows on long timescales, but they could not say, we see the correlation. Because seeing correlation requires three things at once: a large number of stable pulsars, a long observing baseline, because low-frequency waves demand long time, and enough control over noise sources that your residuals are not dominated by the wrong kind of drift. The baseline is unforgiving. A background in the nanohertz band means periods of years to decades. You cannot cheat that with a better telescope. You cannot buy your way out with a bigger mirror. You need time. You need patience. You need to stare at the same pulsars again and again until your data becomes longer than your doubt. And while you wait, the universe fights you with subtlety. Pulsars glitch. Not often, but enough to ruin a clean model. Some pulsars show timing noise that looks smooth until it is not. Some are contaminated by unmodeled companions. The interstellar medium is not a stable vacuum. It is a living weather system. Plasma density changes with solar activity and with the motion of clouds through the line of sight. If you do not observe at multiple radio frequencies and track dispersion precisely, you can confuse plasma changes for gravitational waves. Then there's the solar system. The barycenter correction depends on knowing planetary masses and orbits. We know them well, but in this game, well is not always enough. A tiny error in Jupiter's mass or orbit can shift the barycenter. That shift affects every pulsar's timing in a way that looks common. In early analyses, ephemeris uncertainty was one of the biggest ghosts. It was the kind of mistake that could create an illusion of a background without any waves in the sky at all. So teams had to do something uncomfortable. They had to treat the solar system as part of the noise model, not a fixed truth. They had to allow for ephemeris uncertainty and marginalize over it. They had to test multiple ephemerides. They had to ask, if I tweak the solar system within its uncertainty, does my signal survive? And they had to confront the most humiliating possibility: a clock problem. Because a pulsar timing array is built from Earth-based clocks. If your time standard drifts, every pulsar inherits that drift. A common red noise process could be a cosmic signal, or it could be you. This is why independent observatories matter. This is why cross-checks matter. This is why you do not declare victory until the same signature persists across different instruments, different pipelines, different methods. When people imagine discovery, they picture a single night, a single plot, a single moment where the universe reveals itself cleanly. This discovery does not work that way. It is a slow accumulation of confidence. It is data arriving month after month, year after year, until a probability distribution tightens like a noose. When the timing arrays began reporting evidence of a common spectrum, it was exciting but not decisive. Because the universe is full of common things, the question was whether the common process was also correlated in the right way. That required more pulsars, and it required more time, and it required more careful modeling of noise than most fields ever need. Then, slowly, correlation began to appear. Not as a perfect curve at first. Nothing is perfect at first. It appeared as a preference, as a trend. As data that increasingly favored the spatial correlation expected from gravitational waves over simpler alternatives. This is the moment the story changes. Because once correlation emerges, you stop debating whether the hum exists. You start debating what it is made of. A gravitational wave background is not a single source. It is an entire population, and populations carry information. The overall amplitude tells you how loud the universe is in that band. The spectral slope tells you how the power is distributed across frequencies, which depends on how binaries evolve and what environment they live in. The anisotropy, the patchiness across the sky, tells you whether the background is made of many faint sources or a few dominant ones. If a few binaries dominate, You might eventually resolve individual contributions. If many contribute, the background remains smooth. Even the slightest mismatch between observation and expectation becomes a lever that pries open cosmology. If the background is stronger than predicted, then perhaps supermassive black hole binaries are more common than models suggest. That would imply more galaxy mergers, earlier mergers, faster sinking of black holes into the center, more efficient hardening. It could mean the so-called final parsec problem, the idea that binaries might stall before gravitational waves take over, is not as severe as feared. Or it could mean gas disks and stars conspire to drive binaries inward more efficiently than simulations assumed. But if the background is weaker than predicted, that is also a crisis. It could mean binaries stall. It could mean supermassive black holes do not pair up as often as expected. It could mean galaxy merger rates are different. It could mean our assumptions about black hole demographics are wrong. It could mean we have been counting the universe incorrectly. And then there is the most unsettling possibility. The background does not have the slope we expect from black hole binaries at all. A population of supermassive black hole binaries tends to produce a characteristic power law spectrum in this band. If the observed spectrum bends or flattens or shows features that do not match, then astrophysics alone may not explain it. Suddenly, the conversation shifts toward early universe physics. Cosmic strings would generate a background with different properties. Early universe phase transitions could imprint bumps and knees. Inflationary relics would carry their own signature. These sources are not just alternative explanations. They are a different kind of message. They would mean the hum is not a record of galaxy mergers. It is a fossil from the first moments of reality. And that is why the curve matters so much, because the curve is the doorway. Once you walk through it, you do not get to go back to treating the universe as silent. You have a new channel, a new sense, a new way to test what the cosmos has been doing while light was distracted. But there is one more complication, and it is the one that keeps experts cautious even as evidence grows. A gravitational wave background can exist and still be misread, because what you measure is a mixture. A mix of the Earth term, the effect of waves passing near Earth, and the pulsar term, the effect of waves passing near each pulsar long ago. The pulsar term is like a delayed echo from thousands of years in the past, because the pulsars are thousands of light years away. It adds complexity and richness, but it also adds confusion. It makes the background both a present-time measurement and a historical record. This is not just a signal. It is a time machine. If you can disentangle these pieces, you can learn more than the existence of the hum. You can map it. You can localize dominant contributors. You can begin to see whether the background is smooth or whether it contains bright points, the loudest pairs in the cosmic choir. That is the next horizon. Not just detection, not just correlation, characterization. And characterization leads to a question that sounds like astronomy, but is actually about how the universe builds its biggest monsters. If supermassive black hole binaries are responsible, then every major galaxy merger across cosmic time is part of this hum. Every collision of galaxies carries its black holes inward. Every time two galactic cores combine, the center becomes a staging area for a binary that may live for millions of years. The background becomes the sum of all that history, which means the hum is not random. It is narrative. It is the story of structure becoming structure, the story of the universe preferring larger, heavier, more bound configurations. But a story like that has a missing chapter. A gap between galaxies merge and black holes merge. A stage where the binary must lose energy and angular momentum, where it must shrink from a loose pair to a tight system dominated by gravitational wave emission. That gap is where many models have struggled. In the next part, we go into that gap. We follow the life of a binary in the heart of a merged galaxy. We trace the stages where it should stall and the mechanisms that might save it. We confront the final parsec problem, the question that decides whether the universe should be humming as loudly as it seems to be humming. Because if binaries stall, the background should be quiet. If binaries do not stall, then the universe has been merging its biggest black holes far more efficiently than we thought. And either way, the hum is about to force a rewrite. Massive black hole binary does not begin as a binary. It begins as an aftermath. A galaxy merger is not two neat disks politely overlapping. It is a slow collision where gravity rearranges everything. Stars are flung into long tidal streams. Gas clouds slam together, compress, heat, ignite. The cores sink inward like heavy stones in a cosmic ocean, and deep inside each core, a black hole rides along as the densest passenger. At first, the two black holes are far apart, separated by thousands of light years. They do not orbit each other yet in the way people imagine. They are just two massive objects moving through a sea of stars and gas, losing energy through drag. Not air drag, gravitational drag, dynamical friction. Every time a black hole passes through the stellar crowd, it focuses stars behind it into a wake, a slightly overdense trail. That wake tugs back on the black hole, stealing orbital energy and slowing it down. The black holes spiral inward, not because they choose to, but because the galaxy refuses to let them keep their momentum. This stage is almost guaranteed. It is the easy part. The galaxy is dense, the black holes are heavy, and dynamical friction is efficient. Over time, the separation shrinks from thousands of light years to hundreds to tens, until the two black holes enter the same gravitational neighborhood. Eventually, they become bound. Now the word binary finally becomes real. But here's where the story stops being easy. Once the black holes are close enough to form a bound pair, the nature of the drag changes. Dynamical friction weakens because the binary begins to behave like a single massive object to distant stars. The wake becomes less effective. The binary still needs to lose an enormous amount of energy and angular momentum to shrink further, to reach the regime where gravitational wave emission dominates. And between those two regimes lies a bottleneck. A narrow, dangerous corridor in the evolution. The stage where, in theory, the binary should stall. This is the final parsec problem. A parsec is a little over 3 light years. In a galactic nucleus, a separation of about a parsec is the scale where the binary is tightly bound, but still too wide to radiate gravitational waves strongly enough to merge in a reasonable time. At this scale, the binary must continue shrinking through interactions with its environment. It must hand off energy to stars and gas. It must harden, meaning its orbit must tighten. But the mechanisms that harden it can run out of fuel. The main fuel at this stage is stars. Imagine the binary as a gravitational slingshot. A star wanders too close to the pair. It falls into their combined gravitational field and interacts with their orbit. The star can steal a tiny amount of orbital energy from the binary and get flung outward at higher speed. The binary loses energy and tightens. Repeat this millions of times and the separation shrinks. This sounds straightforward until you ask the obvious question. Where do the stars come from? Only stars that pass close enough matter. Only stars on the right kinds of orbits can enter the binary's loss cone. The set of trajectories that bring them into the danger zone where the slingshot works. The binary empties this region quickly. It ejects stars. It scours the nucleus. It carves out a low-density core. The immediate supply is depleted. If the galaxy nucleus were perfectly spherical and perfectly calm, replenishing the loss cone would be slow. Stars on safe orbits would not easily scatter into dangerous ones. The binary would run out of targets. It would stall at roughly parsec scale, orbiting forever, too wide to merge, too tight to be separated, a frozen pair of monsters locked in an eternal dance. That is the final parsec problem. The idea that the universe might create binaries efficiently, but merge them inefficiently. And here is why this matters. If binaries stall, then the gravitational wave background in the nanohertz band should be different. It could be weaker. It could be shaped by a pileup of stalled systems. It could carry the signature of a universe that makes pairs but does not finish the job. But the evidence for a hum suggests the universe might be finishing the job, or at least finishing it often enough to matter. which means the final parsec problem, if it exists, is either solved by the universe or solved by our ignorance. So what saves the binary? The first answer is that real galaxies are not perfectly spherical. A galaxy core is not a smooth ball of stars. It is a living gravitational field shaped by mergers, triaxial distortions, bars, rotating structures, and the scars of past violence. In a non-spherical potential, stellar orbits are not simple closed loops. They can be boxy, they can wander, they can bring stars into the center naturally without relying on slow two-body relaxation. The loss cone can be refilled not by rare scattering events, but by the geometry of the galaxy itself. In other words, the galaxy can funnel stars toward the binary simply because it is not symmetric enough to be stable. The same chaos that built the galaxy can keep feeding the binary with fresh targets. Another answer is that the binary does not live in a vacuum of stars alone. After a merger, gas can fall inward, gas can cool, form a circumnuclear disk, and create a dense rotating environment around the binary. A gas disk is not just mass, it is a machine for moving angular momentum. Viscous torques, shocks, magnetic turbulence, and gravitational instabilities can transport angular momentum outward, allowing matter to drift inward. If the binary interacts with this disk, it can transfer angular momentum to the gas, tightening its orbit. This is analogous to planet migration in young planetary systems, where a planet exchanges angular momentum with a protoplanetary disk and moves inward. In the galactic core, the scale is vastly larger, but the principle rhymes. Gas can also do something else. It can drive eccentricity. A circular orbit shrinks steadily under gravitational wave emission, but an eccentric orbit shrinks faster at closest approach. Eccentricity concentrates gravitational wave power into bursts near pericenter, effectively accelerating the merger. If environmental interactions pump eccentricity, a binary can reach the gravitational wave-dominated regime sooner than a circular model would predict. And then there is a darker, more chaotic possibility. A third black hole. Galaxies do not merge once, they merge repeatedly. If a galaxy with a binary black hole later merges with another galaxy carrying its own central black hole, you can get a three-body interaction. Triples are unstable. They exchange energy violently. One black hole can be flung outward. The remaining pair can tighten dramatically. This is not a gentle process. It is a gravitational bar fight, but it is efficient at hardening binaries. This mechanism does not need gas. It does not need perfect stellar feeding. It needs a universe that keeps merging, which the universe happily provides. So the final parsec problem is not one problem. It is a question that depends on context. It depends on whether the nucleus is triaxial. It depends on whether there is gas. It depends on whether the galaxy experiences repeated mergers. It depends on how stars are distributed and how quickly their orbits diffuse. And that means the gravitational wave background becomes a test of galactic nuclei physics, a test of environments we can barely resolve with light alone, because the background is not just, are there binaries? It is, how do binaries evolve? Here's the crucial idea. If a binary evolves purely under gravitational waves, its frequency increases in a specific way. Its power spectrum follows a characteristic slope. But if the binary is strongly influenced by its environment at low frequencies, by stars, by gas, by dynamical friction, then the spectrum can change, it can bend, it can turn over. The background can be suppressed at the lowest frequencies if binaries spend less time there, or enhanced if they linger. It can reveal whether the universe accelerates binaries through the bottleneck or leaves them to drift. This is why the nanohertz band is so valuable. It sits exactly in the regime where environmental effects should matter. It is not the final seconds. It is not the final scream. It is the long, slow tightening where astrophysics fights gravity for control of the orbit. In a simplified picture, there are stages. Stage 1 is dynamical friction. The black holes sink toward the center after a galaxy merger. The orbit shrinks until the pair becomes bound. Stage 2 is stellar hardening. The binary interacts with stars passing close by, ejecting them and shrinking. Stage 3 is environmental coupling. Gas disks, non-spherical potentials, and repeated perturbations continue to refill the loss cone and extract angular momentum. Stage 4 is gravitational wave domination. The binary becomes tight enough that its own radiation of spacetime ripples does the rest. If the universe flows through these stages smoothly, the background should reflect an efficient merger pipeline. If the universe jams at stage 2 or 3, the background should look different. And if some galaxies are gas-rich while others are gas-poor, if some nuclei are triaxial while others are near-spherical, then the background might not be perfectly smooth. It might contain anisotropy, it might be dominated by a small number of bright contributors. This is where the background stops being an abstract hum and becomes something almost visual. Because a background can be smooth like fog, made of countless faint sources, or it can be lumpy like a skyline, where a few tall towers dominate the light. If the skyline version is true, then something extraordinary becomes possible. You could resolve individual binaries, not with images, with timing. A single very massive nearby binary could imprint a quasi-periodic signature across multiple pulsars, a coherent wave rather than a stochastic background. It would be like hearing one singer stand above the crowd. The first resolved supermassive black hole binary would be a historic event, not because it would be dramatic on screen, but because it would turn the background from a statistical field into a catalog. It would let you point and say, this galaxy, this core, this orbit, this is what the hum is made of. But before that happens, we need to understand what kind of universe we live in. A universe where binaries stall would be full of ghosts, pairs locked in place, orbiting without ever merging. A universe where binaries merge efficiently would be full of completed stories, pairs that tighten, cross the threshold, and vanish into a single black hole. Which universe fits the hum? The answer depends on details we do not yet fully control. And that is exactly why the hum is powerful. It forces those details into the open. It is easy to build a theory of galaxies using light, because light shows you what exists now. It shows you stars and gas and dust. It shows you the present shape, but it does not directly show you the hidden dynamics in the core. The black holes are too small, too distant, too buried. You infer them from indirect signals. Gravitational waves do not give you a picture. They give you the orbit itself. They turn the invisible into measurable motion. If the background continues to harden into certainty, and if its spectrum and spatial structure become clearer, then the final parsec problem stops being a debate. It becomes a measurable property of the universe. And that leads to the next question, which is even more unsettling. If supermassive black hole binaries are merging efficiently, then the universe has been doing something violent and frequent for billions of years. It has been combining the central engines of galaxies. It has been rewriting the deep structure of galactic cores. This implies not just mergers, but recoil. When two black holes merge, the gravitational waves they emit are not always perfectly symmetrical. If the radiation carries away net momentum in one direction, the remnant black hole receives a kick in the opposite direction, a recoil velocity. In extreme cases, that kick can be large enough to displace the black hole from the galaxy's center, or even eject it entirely if the galaxy's gravitational well is not deep enough. A universe that merges black holes efficiently is a universe that sometimes throws them away. If this happens, it changes galaxy evolution, it changes core dynamics, it changes how central black holes regulate star formation and gas inflow. It changes what a galaxy even means when its central engine can be knocked off its throne. So the hum is not just a measurement of mergers, it is a measurement of consequences. In the next part, we widen the lens, we follow what the hum implies about the population itself. How many binaries? How massive? How close? How loud? We look at what a background can reveal about the history of galaxy mergers and why this new channel might collide headfirst with the stories we told ourselves from light alone. Because once you can hear the universe, you are no longer limited to what it shows you. You can ask what it has been doing behind the curtains, and you can demand answers that images cannot give. Once you accept the hum, you inherit a new kind of astronomy. Not the kind where you point a telescope and collect photons, the kind where you point at nothing and collect statistics. A gravitational wave background is not a single event, it is a population speaking at once. And populations always tell on themselves. They reveal how common something is, how extreme it gets, how it changes with time. The background becomes a census you never asked for, a ledger the universe kept without permission. The first number everyone reaches for is amplitude. How loud is the hum? Because loudness is not just a measurement, it is a consequence. If the background is louder than expected, it implies more binaries, heavier binaries, closer binaries, or binaries that spend more time radiating in the band you can hear. In other words, it implies a universe that builds supermassive black hole pairs efficiently and pushes them through the bottleneck without stalling too often. It implies that mergers are not rare accidents. They are routine. If the background is quieter than expected, that is not comforting either. That would imply the opposite. Binaries stall. The final parsec problem wins more often, or the supply of truly massive pairs is smaller than we thought. Or galaxy mergers do not translate into black hole mergers the way our stories assume. Quietness would mean something is missing in our model of how galactic cores behave. It would mean the universe is not finishing the job, but amplitude alone is only the opening line. The next clue is the slope, how the power changes with frequency. The hum is not flat, it has shape. And shape is where the physics hides. A background dominated by supermassive black hole binaries evolving under gravitational radiation tends to follow a characteristic trend across frequencies. But real binaries do not evolve in a vacuum. Stars harden them, gas torques them, triaxial potentials refill their loss cones, triples kick them. Each of those processes reshapes how long a binary spends at each separation, and therefore how much gravitational wave power piles up in each frequency band. If binaries linger at wide separations, the lowest frequencies get heavier. If they rush through wide separations, the lowest frequencies get thinner. If environment drives eccentricity, power can shift. If gas dominates early, the spectrum can bend. A bend is not a detail, a bend is an accusation. It points directly at the mechanism doing the work, so the hum becomes a probe of the invisible. It becomes a way to interrogate a region no image can fully resolve. The inner parsec of galaxies, the place where black holes live behind dust, behind stars, behind time. And then comes anisotropy. The question nobody wants to answer too early because it turns the background into a map. People say background and imagine something uniform, smooth, the same in every direction. But the universe is not uniform on the scales that matter to gravitational wave loudness. Massive galaxies cluster. Mergers are not evenly distributed across the sky. The loudest binaries are not sprinkled like random sand. They are tied to structure. They are biased toward the heaviest environments, groups, clusters, regions where galaxies collide more often. If the hum is made of countless faint sources, it will be smooth like fog. If it is made of fewer, louder sources, it will be lumpy. And lumpiness changes everything. Because a lumpy background is not just a measurement, it is a hunting ground. In a lumpy universe, the brightest contributors are close enough and massive enough that they might not fully blend into the crowd. They might leave an imprint that is not purely stochastic, a continuous wave, a slowly varying, almost periodic signature that persists across years. It would be the universe whispering one name through the noise. This is where the story starts to feel like a crime investigation. You do not look for one clear signal. You look for a pattern that refuses to average out, a coherent strain that repeats, a phase that lines up across pulsars the way only a real wave could. And if you find it, you do not get an image, you get a direction, a patch of sky, a probability cloud. Then you do something we have never been able to do cleanly before. You point light at the answer. Multi-messenger astronomy in this band is not guaranteed, but it is tempting in a way that borders on addiction. Because if you could link a gravitational wave source to a real galaxy, you would be watching the core engine of a merger not through brightness, but through motion. You would know a binary exists because spacetime says so. And then you would search for signs of its environment, a disturbed nucleus, peculiar emission lines, unusual periodicity, a quasar that flickers in a rhythm, a galaxy core with scars. Even if you never see the black holes directly, you would see their consequences. And consequences are enough. This is the deeper threat the hum poses to the old way of doing cosmology. Light-based astronomy infers supermassive black holes through proxies, through the glow of accretion, through stellar velocity dispersions, through relationships that look stable and universal until you look far enough back in time and the relationships start to break. We already know from the early universe that black holes can outrun their galaxies, that the normal ratios can be violated, that growth can be weird. The hum is an independent accounting system. It does not care about how bright a quasar looks. It does not care about dust obscuration. It does not care whether an active nucleus is turned toward us. It measures the existence of binaries by their gravity alone, which means it can reveal a population of systems that light might miss, and it can expose biases we did not know we had. If the background implies more binaries than our electromagnetic surveys would suggest, that is not a small discrepancy. That is a crisis of demographics. It would mean we have been undercounting the number of supermassive black holes that are paired and evolving. Or it would mean that the pairing phase is longer, that binaries spend more time in the nanohertz band than models predict. Or it could mean something stranger, that some portion of the hum is not astrophysical at all, because there is always the other door. A background can be primordial. Cosmic strings, if they exist, would radiate gravitational waves across a wide range of frequencies, and a network of them could contribute a stochastic background with different statistical fingerprints. Early universe phase transitions could do it too, violent moments when the vacuum reconfigured, releasing energy into space-time ripples. Inflationary relics could leave an even older imprint, a fossil hum from the earliest instance. In that scenario, the hum is not the story of galaxies, it is the story of creation. The distinction is not poetic, it is testable. Astrophysical backgrounds and primordial backgrounds tend to differ in spectral behavior, in anisotropy, in non-Gaussianity, in how lumpy they are. A background built from a few loud binaries is not the same as a smooth primordial field. One looks like a skyline, one looks like mist, and mist would be terrifying. Because it would mean the hum is not telling us about the centers of galaxies, it is telling us about the physics of the early universe, about energy scales we cannot reach in particle accelerators, about fields we have never seen, forces we do not know how to name. So the hum forces a fork in the road, and the fork is not resolved by belief. It is resolved by more data, longer baselines, more pulsars, better models, and the one thing the universe does not care that you lack: time. But while we wait for that fork to sharpen, the hum is already doing something else. It is pressuring our narrative about how the biggest black holes grow. If supermassive black hole binaries are common and merging efficiently, then the universe has been consolidating its central engines across cosmic history. That means every major galaxy merger is not just a visible spectacle of stars and gas, it is a gravitational negotiation, a slow tightening in the core that ends in a violent fusion we cannot see with light at all. And that implies recoil. Because when the final merger happens, the remnant black hole can be kicked, not metaphorically, physically. The asymmetry of gravitational wave emission can launch it away from the center. Sometimes it settles back. Sometimes it oscillates for millions of years. Sometimes, in smaller galaxies, it can be ejected entirely. A universe that merges black holes is a universe that sometimes loses them. That possibility changes the way you think about galaxies. It means some galaxies may carry the scar of an absent center. Means some galaxies might have undergone a phase where the central engine was displaced, altering feedback, altering star formation, altering the fate of the gas. It means the black hole in the middle is not guaranteed to remain in the middle forever. And now, the hum starts to feel less like a curiosity and more like a lever. Because once you can measure the merger rate, the mass distribution, and the efficiency of the pipeline from pair to merger, you can test entire models of galaxy evolution from the inside out, not by looking at the result and guessing the cause, but by measuring the cause directly in the language of gravity. The hum is not just telling us that binaries exist, it is telling us how the universe processes violence into structure. In the next part, we push this to its edge. We ask what happens when the hum stops being a background and starts becoming a set of individual suspects. We explore the possibility that one nearby, massive binary might already be loud enough to isolate, and we follow what it would mean to identify it, to tie spacetime ripples to a specific galaxy, to turn the oldest invisible dance in the universe into a measurable orbit. Because once you do that, you are no longer listening to the crowd. You are listening for a single voice. A background is a confession, but it is also camouflage. When thousands of sources overlap, everything becomes statistical. You stop seeing faces, you only see crowds, and yet the universe does not distribute its violence evenly. If the nanohertz hum is built from supermassive black hole binaries, then the loudest contributors should not be average. They should be rare, heavy, close enough to matter. They should be the kind of systems that dominate not because there are many of them, but because one of them can outweigh 1,000 quieter pairs. That is the first crack in the word background, because a background can be smooth, or it can be grainy. And graininess is where individual voices can emerge. In the simplest picture, imagine a choir so large you cannot pick out a single singer. Then, imagine one voice is not just louder, but closer. Its sound does not blend. It bleeds through. The crowd is still there, but now the noise has a spine, a coherent tone that refuses to average away. That coherent tone is what pulsar timing arrays call a continuous wave. It is not the brief chirp of stellar mass black holes. It is a slow, almost stubborn oscillation in spacetime, driven by two supermassive black holes orbiting each other on timescales of years. Their orbit is so wide that their gravitational wave frequency is low, and their evolution is slow. They do not race upward in frequency in your lifetime. They just keep turning like a lighthouse that never shuts off. If you could isolate one, it would be more than a detection. It would be the first time we measure the orbit of a supermassive black hole binary directly through gravity, not inferred from light, not guessed from periodic flickers, measured. But isolating one is cruelly difficult, because a continuous wave does not arrive with a name attached. It arrives as a pattern in timing residuals spread across pulsars, a coherent deformation whose signature depends on where the source sits in the sky, the orientation of its orbit, and how its polarization projects onto your pulsar network. And your pulsar network is not a perfect array of sensors. It is an irregular constellation of clocks, unevenly distributed across the sky, each with its own noise, each with its own quirks, each observed by instruments that have changed over decades. This is not a clean interferometer. It is closer to a jury trying to agree on a whisper they heard through walls. So the search becomes mathematical. You build templates for what a continuous wave would do. You scan sky positions, you test frequencies, you compare models, you ask whether the data prefers just noise or noise plus a coherent wave. And you do it while respecting the fact that nature loves to imitate your hopes. Because periodicity is a siren song. Many things can look periodic if you stare long enough. Sampling cadence creates aliases. Seasonal observing patterns can imprint year-like signals. Solar wind variations can introduce slow distortions. A single problematic pulsar can produce a coherent-looking artifact that vanishes when you remove it. This is why continuous wave claims are the hardest kind. They demand not just a signal, but resilience under every skeptical attack you can invent. And even if a continuous wave exists, localization is not what people imagine. You do not draw a circle around a star and say, "It is there." You get a patch. Sometimes a large patch, sometimes a patch with multiple islands. A probability sky map that tells you where the wave could be coming from. It is a direction, not a portrait. It is enough to aim telescopes, but not enough to be sure you have found the guilty galaxy. This is where multi-messenger astronomy becomes both tempting and dangerous. Because once you have a sky patch, you can go hunting in light. You can look for galaxies that are massive enough, close enough, disturbed enough. You can search for active galactic nuclei that show hints of binary behavior. You can search for quasars with unusual periodic variability. You can search for dual cores, offset emission lines, warped jets, anything that smells like two central engines locked in orbit. But light is a biased witness. Many supermassive black hole binaries will not be bright in the way we expect. They may be shrouded in dust, they may be in a low accretion state, they may be quiet. The gravitational wave does not care. The orbit exists regardless of whether it is glamorous, so the best-case scenario is not one where light hands you the answer. The best case is one where light and gravity meet in the middle. A gravitational wave localization narrows your search. Electromagnetic clues rank the suspects, and together they make a case strong enough to stand in court. Even that is not simple, because the wave you measure is not only from near Earth. A pulsar timing array signal contains two ingredients: the Earth term, the effect of the gravitational wave passing near Earth now, imprinting a coherent signature shared across pulsars, and the pulsar term, the effect of the wave passing near each pulsar thousands of years ago, imprinting a delayed echo unique to each line of sight. The Earth term is your present tense. The pulsar term is your ancient history. The pulsar term complicates detection, but it also offers a terrifying possibility. If you can measure it well, it gives you additional information about the source, because you are effectively sampling the wave at 2 times separated by thousands of years. For a continuous wave source, that means you could, in principle, see the binary's frequency at the pulsar long ago and compare it to the frequency now. You could measure how the orbit has evolved across millennia. You are not just detecting a binary, you are tracking it through time. This is the moment the story shifts from "we hear a background" to "we can do gravitational wave astrophysics at the centers of galaxies." And the moment you say that, a new problem appears. If there are individual loud binaries, why have we not already seen them in light? The answer might be simple. We have seen them, but we did not know what we were looking at. Many candidates have been proposed over the years, from periodic quasar variability or peculiar emission line behavior. Some of those candidates will turn out to be false positives because accretion disks can vary for reasons unrelated to binaries. Jets can precess, dust can obscure. The central engine is chaotic. It can imitate a heartbeat without having 2 hearts. But the answer might be darker. The loudest binaries could be electromagnetically quiet. A binary can be strong in gravity and weak in light if it has little gas, if it lives in a depleted nucleus where the merger expelled or heated the fuel, if the accretion flow is low, if the orbit has carved a gap in a circumbinary disk that starves both black holes, if the system is in a phase where it is an efficient radiator of spacetime ripples but an inefficient radiator of photons. In that case, gravitational waves are not just an additional channel. They are the only honest channel. And that changes how you think about the universe's hidden inventory. It means there could be massive binaries in our cosmic neighborhood that are not shining like beacons, not flaring like quasars, not announcing themselves the way we trained ourselves to expect. They are simply there, moving, silent in light, loud in gravity. The background, then, is not a wall of noise. It is an invitation to find what our telescopes did not know to look for. But there is an even stranger consequence of a grainy background. A grainy background is not just the sum of many binaries. It is a battlefield of interference. Different sources overlap. Their phases mix. The background can deviate from simple Gaussian statistics. It can contain non-Gaussianity, a signature of dominance by a few contributors rather than a sea of countless weak ones. In principle, the data itself can tell you whether the hum is fog or skyline. Fog implies too many singers. Skyline implies a few giants. And skyline implies you are closer than you think to resolving the first individual system. But a first resolved system would not be the end. It would be the beginning of a new catalog, Once you know how to find one, you know how to find more. You refine your pulsar set, you improve cadence, you target the sky regions with best sensitivity, you extend the baseline, you build methods that separate the stochastic crowd from coherent notes. And as that catalog grows, you gain a new kind of leverage, because every individual binary comes with parameters: sky location, frequency, amplitude, polarization, and potentially evolution. Those parameters translate into physical quantities: chirp mass, distance, inclination, and environmental coupling. You can begin to test whether binaries evolve as pure gravitational wave sources or whether stars and gas still matter. You can measure whether eccentricity exists in the population. You can test the final parsec problem not only statistically but case by case. This is the pivot. The moment the hum stops being one number and becomes many stories. And those stories do not stay contained. They collide with galaxy evolution. If you detect a nearby, loud binary, the host galaxy is almost certainly massive. Massive galaxies live in dense environments. Dense environments are where mergers are common. Those environments shape star formation, gas inflows, and feedback. The binary is not an isolated system. It is a product of a merger history. So identifying even one source would let you connect a gravitational wave measurement to a specific galaxy's visible scars. You could compare what the galaxy looks like to what the orbit implies. You could test whether the galaxy's nucleus is gas-rich or gas-poor. You could search for disrupted stellar cores and scour density profiles. You could look for signs of past ejections. You could do forensic astrophysics on a living system whose central engine is literally shaking spacetime. And it would force another uncomfortable question. If binaries are this common, if the hum is this real, then mergers are not rare events that happened sometimes. They are a dominant engine of cosmic evolution, which means the universe has been manufacturing remnant black holes with kicks, offsets, oscillations, and in some cases, escapes. A merger does not always end with a remnant sitting politely at the center. It can end with a recoil, a remnant launched from the core by asymmetrical gravitational wave emission. The recoil velocity depends on mass ratio and spins, on how the two black holes were oriented as they merged. Under certain configurations, the kick can be huge, enough to displace the black hole far from the center, enough in smaller galaxies to eject it entirely. Now, combine that with a loud merging universe. You get a cosmos where some galaxies may have lost their central engines. Others may have engines that are offset. Others may have engines that returned after wandering. Others may be in a transitional state where the black hole is not where you expect it to be. Those would be invisible in most surveys because we search for nuclei. We search for centers. We assume the king sits on the throne. A universe that hums loudly is a universe where the throne is sometimes empty. That is not metaphor. That is prediction. And if that prediction is correct, it has consequences for everything we think black holes do to galaxies. Feedback depends on position. A displaced black hole does not heat gas the same way. It does not regulate star formation the same way. It does not sculpt the bulge the same way. It changes the story of how galaxies become quiescent. It changes how cores evolve. It changes what it means for a galaxy to be normal. So the hunt for one voice is not a side quest. It is a gateway to rewriting the relationship between galaxies and the black holes they are built around. But before that rewrite can happen, the background itself must survive its harshest test, because there is still an alternative that refuses to die. What if the hum is not made of binaries? What if it is primordial? A primordial background would not care about galaxies. It would not correlate with cosmic structure the same way. It would not be lumpy because of local massive environments. It would be closer to isotropic. It would have its own spectral signature, its own statistical fingerprints. And if even a fraction of the hum is primordial, then what you are hearing is not the centers of galaxies. You are hearing the early universe. In the next part, we step into that fork in the road. We take the hum seriously enough to ask which universe it implies. An astrophysical universe dominated by merging supermassive black holes. or a deeper universe where the hum contains fossils from creation itself. We trace the signatures that could separate skyline from mist, late-time mergers from early-time physics, and we confront the possibility that the hum is not just telling us how galaxies merge. It is telling us what reality did before galaxies existed. The hum gives you a choice you do not get to avoid. Either it is the sound of galaxies colliding and black holes finishing the job, or it is something older, something that does not care about galaxies at all. This is the fork in the road. On one side is an astrophysical universe, a universe where the background is the combined gravity of supermassive black hole binaries, countless pairs across cosmic time, tightening in the dark cores of merged galaxies. The hum is history written in mergers, a ledger of how often structure collided and consolidated. On the other side is a primordial universe, a universe where the background is not a crowd of late-time binaries, but a fossil field, ripples seeded when the universe was young enough that galaxy was not even a concept. In that universe, the hum is not a census of black holes, it is a remnant of the early cosmic machinery. Phase transitions, exotic defects, unknown fields, physics that never repeated. Both possibilities are terrifying because both rewrite something fundamental. The astrophysical answer rewrites how galaxies evolve at their cores. It forces you to admit that supermassive black holes merge efficiently enough to fill the universe with a measurable gravitational murmur. It elevates the hidden centers of galaxies from a footnote to the main engine of cosmic history. The primordial answer rewrites something deeper. It means the early universe left behind a measurable imprint in the nanohertz band, a kind of echo that survived 13.8 billion years of expansion and still shakes your clocks today. It means the hum is a message from creation, and the message is written in physics we do not yet understand. So how do you tell which universe you are in? You do not do it with one headline number. You do it with fingerprints. The background has to betray its origin, because different origins cannot help but leave different structure in the data. The first fingerprint is shape, not the vague idea of its red noise, but the detailed way power is distributed across frequency. Supermassive black hole binaries, under a clean gravitational wave-driven evolution, tend to create a characteristic trend. But the moment you add real astrophysics, stars scattering, gas torques, eccentricity pumping, the shape can bend. It can flatten at low frequencies if binaries are being driven through the wide separation regime by environmental processes. It can steepen or show subtle features if a population spends unusually long in certain evolutionary stages. A primordial background, on the other hand, is not built from individual orbits in galactic nuclei. It is built from early universe processes, and early universe processes often produce different spectral behaviors, sometimes smoother, sometimes with knees, sometimes with slopes that do not match the simple expectation of a binary population. Shape is not proof, but shape is a clue. The second fingerprint is texture. This is where the word fog finally matters. A background made of countless weak sources tends to be close to Gaussian, random enough that when you average, nothing sticks out. A background dominated by fewer loud sources becomes non-Gaussian. It becomes grainy. It contains rare bursts of dominance. It has statistics that look less like a smooth field and more like a skyline. Supermassive black hole binaries can create skyline behavior because the loudest contributors are not evenly distributed. A few massive nearby pairs can dominate. That makes the background lumpy, and lumpiness makes it possible, eventually, to resolve individual systems as continuous waves. A primordial background tends to be closer to fog. Not always perfectly, but often. If the background is truly primordial, you expect less domination by a few nearby monsters. Because there are no nearby monsters, there is just a field. So the data has to answer a brutal question. Does the hum look like a crowd of sources or a smooth ocean? Fog or skyline? The third fingerprint is direction. An astrophysical background should trace structure, not perfectly but statistically. The loudest contributions should correlate with where massive galaxies are, with where mergers happen, with where the local universe is dense. Over time, with enough pulsars and enough baseline, you should be able to test whether the background is isotropic or anisotropic, whether it is the same in all directions or stronger in certain regions of the sky. A primordial background has no reason to care about the distribution of galaxies today. If it is truly primordial and roughly uniform, its anisotropy should be weaker and shaped by entirely different physics. The sky pattern becomes a test, not a simple one, but a real one. And that brings you to the fourth fingerprint, the most merciless one: correlation geometry. A true gravitational wave background must imprint a specific angular correlation across pulsars. That is the doorway you already walked through when the evidence for correlation began to rise. But once that doorway is open, you can ask a sharper question. Is the correlation consistent across frequency? Is it stable as the pulsar set changes? Does it strengthen as baseline grows? Does it behave like a genuine spacetime field rather than an artifact of a clock error, an ephemeris mismatch, or an unmodeled plasma trend? Because the path to truth here is not romance, it is repetition. A real signal survives abuse. It survives different analysis pipelines. It survives different observatories. It survives removing one problematic pulsar. It survives changing noise models. It survives the skeptical urge to assume you are fooling yourself. A fake signal dies under that pressure. A real one hardens. Now, here is the complication that makes this fork harder than people want it to be. The universe is allowed to be both. The background you detect does not have to come from one source class only. It can be a mixture, a dominant astrophysical contribution with a subdominant primordial component hiding underneath, or a primordial field with an astrophysical layer on top. The hum could be a composite sound. And composite sounds are dangerous because they can imitate simpler ones until you have enough sensitivity to separate them. This is why the next decade matters so much in this story. Not because someone will flip a switch and announce it's binaries, not because someone will publish a paper and solve it, but because the discriminants improve with time in a way few other experiments experience. A pulsar timing array grows more powerful the longer it exists. The lowest frequencies become accessible only with longer baselines. The ability to see spectral bending improves. The ability to test anisotropy improves. The ability to detect non-Gaussianity improves. The ability to resolve individual loud sources improves. Time is not just a resource here, it is the instrument. And as the baseline grows, a new possibility becomes realistic. The possibility that the skyline reveals itself, one continuous wave source, one nearby massive binary that refuses to blend. If you find it, it changes the argument overnight, not because it proves the entire background is astrophysical, but because it proves at least part of it is. It becomes a concrete anchor, a physical system with parameters, a reality you can cross-check with light. You can aim electromagnetic surveys, look for candidate host galaxies, check for disturbed nuclei, look for jets, look for periodic variability, look for dual cores. Even if the source is electromagnetically quiet, its existence as a gravitational system becomes undeniable. And once you have one, you can have more. A catalog begins. And a catalog does something a background cannot. It turns statistics into astrophysics. It turns a hum exists into this is what makes it. It turns the universe from an audio mystery into an orbital archive. But if the skyline refuses to appear, if the background remains smooth, Gaussian, isotropic, stubbornly fog-like, then the primordial door becomes harder to ignore. Because a smooth, misty hum that does not map onto structure, that does not show signs of domination by individual sources, starts to look less like a choir of binaries and more like a field. And a primordial field would be one of the most important discoveries in modern physics. It would mean there is new information about the early universe encoded in gravitational waves at frequencies we can finally access. It would mean the universe left behind an imprint that particle physics cannot reproduce in laboratories. It would mean cosmology is not just missing a parameter, it is missing a component. In that universe, the hum is not just another dataset. It is evidence that the fundamental story of the early universe is incomplete, and that loops back to the deepest theme running through everything we have been talking about, from the impossibly early galaxies to the overgrown black holes to the cracks in our standard model. We keep finding that the universe grows structure faster than we expected. It builds massive things early. It behaves like it had more options than our equations allowed. A primordial gravitational wave component would fit that pattern in a terrifying way. It would imply new physics in the early universe that could also affect structure formation indirectly, through expansion history, through additional energy components, through interactions we have not mapped. In other words, the hum could connect to the same set of mysteries that already surround cosmology: the nature of dark matter, the nature of dark energy, the shape of expansion, the timeline of formation. It could be another thread in the same unraveling tapestry, or it could be the needle that lets us stitch a new one, because there is a version of this story that is not panic. There is a version where the hum is a gift, a new channel, a new sense, a new way to test reality when light becomes biased and incomplete, a method that does not care about dust, does not care about glare, does not care about whether an object is turned toward us. Gravity does not ask permission to be measured. It just happens, and the hum is gravity happening at cosmic scale. In the final part, we bring the fork back to meaning. We take what the hum implies, fog or skyline, binaries or fossils, and we ask what it does to our understanding of the universe we live in. Not as a poetic finale, but as a structural one. Because the moment you can hear spacetime, you are no longer confined to a universe made of images. You are living inside a universe that has a sound, and that sound is telling you one thing with ruthless clarity. Reality is doing more than we thought. A century ago, the universe was silent. Not literally silent, but conceptually. We had light, we had spectra, we had photographs on glass plates and equations on chalkboards. We learned to measure distance, mass, composition. We learned that galaxies exist, that they flee, that space expands. We built cosmology like a cathedral, stone by stone, on the assumption that the universe would tell its story in photons. Now it is telling its story in time. That is what the hum is, not a metaphor, not a vibe. A measurable deformation of spacetime arriving as delays and advances in the ticking of dead stars. A background that does not need to be seen to be real. It only needs to be consistent, correlated, relentless. And the moment you accept that, the rules change. Because you are no longer doing astronomy the old way. You are doing something closer to eavesdropping on the universe's private conversations. The first rule that changes is the meaning of invisible. For decades, we called dark matter invisible because it does not emit light. We called supermassive black hole binaries invisible because they are buried inside nuclei, behind dust, behind glare, behind distance. We called the early universe invisible because the first galaxies were too faint, too redshifted, too remote. Those statements were always temporary. They were definitions of our limitations, not of reality. The hum is a reminder that visibility is not about what exists. It is about what channels you can measure. If the hum is astrophysical, then it means the universe has been running a continuous merger program in its cores for billions of years. And we were only seeing the aftermath in light. We were seeing disturbed morphologies, quenched galaxies, bulge growth, active nuclei flickering on and off. We were seeing effects and writing stories about causes. Gravitational waves reverse that relationship. They let you measure the cause directly. If supermassive black hole binaries are common enough to create a measurable background, then mergers are not a footnote in galaxy evolution. They are the engine. They are the conveyor belt that consolidates mass, shapes nuclei, scours stellar cores, and sometimes ejects the very object that is supposed to sit at the center and regulate everything. A humming universe is a universe where central black holes are not always stationary kings. They can be kicked. They can wander, they can be displaced. In smaller galaxies, they can be lost. The throne can be empty and the galaxy can still exist. That single fact would force revisions across galaxy formation theory, feedback models, quenching models, core structure, the assumed stability of the black hole bulge relationships that we used like laws. A background implies a merger rate. A merger rate implies recoil events. Recoil implies displaced engines. Displaced engines imply altered histories. It is a chain reaction that begins with timing residuals and ends with rewriting how galaxies become themselves. But if the hum is primordial, the rule change is even more profound. Because then, the hum is not telling you about the centers of galaxies. It is telling you about the early universe in a way the cosmic microwave background cannot. The CMB is a photograph of the universe at 380,000 years after the Big Bang. A surface of last scattering, a frozen snapshot. A primordial gravitational wave background would be something else, a vibration, a memory of violence, a record of early physics that never repeats, phase transitions, symmetry breaking, defects, fields rolling down potential landscapes. It would be information about energy scales and dynamics that no accelerator on Earth can reproduce. In that universe, the hum is not just a new dataset, it is a new window on fundamental physics, and that connects to the deeper tension in modern cosmology. We do not know what dark matter is. We do not know what dark energy is. We do not know why the expansion history has cracks. We do not know why the early universe built structure so fast, why massive black holes appeared so early, why some galaxies looked too mature too soon. We keep circling the same reality. Our standard model is powerful, but it is incomplete. The hum is not a contradiction by itself. It is not proof the model is wrong. That is not how science works. But it is a pressure test. It forces the universe to show its hidden population of binaries, or it forces the early universe to show its fossil ripples. Either way, it removes one layer of ignorance and exposes the next. That is what progress feels like when it is real, not comfort. Exposure. The second rule that changes is the relationship between patience and power. Most instruments get better when you build bigger mirrors, cooler detectors, sharper optics. Pulsar timing arrays get better when you wait. The baseline is the lever arm. The longer you observe, the lower the frequency you can probe. The lower the frequency you can probe, the more you learn about the slowest, heaviest dynamics in the universe. This means the experiment is not just technology. It is commitment. It is a bet against impatience. And that bet is already paying because the background is not a single headline. It is a landscape you will map over years. Spectrum, anisotropy, non-Gaussianity. Potentially individual sources. Each layer adds discrimination power. Each layer tells you whether you are living in fog or skyline, whether the choir hides a soloist, whether the hum traces galaxy structure or ignores it. Eventually, the hum stops being something you argue about in papers and becomes something you do astronomy with, a new channel that can be combined with light, with X-rays, with radio jets, with infrared surveys, with future space telescopes. A channel that can point you to systems that light would never flag as special. That is the third rule change. The universe is no longer narrated by one messenger. The universe becomes cross-examinable. Light tells you what's glowing. Gravity tells you what's moving. And sometimes what is moving refuses to glow. That is not poetic. It is the most practical reason gravitational wave astronomy matters. It catches the universe being real, even when the universe is quiet in photons. So what does it all mean? It means the hum is not just an astronomical detection. It is a shift in epistemology, a shift in what we consider measurable, a shift in what we consider evidence, a shift in what counts as a map. We used to map the cosmos with images. Then we mapped it with spectra. Then we mapped it with background radiation. Now we are mapping it with time itself, and time is merciless. It doesn't care about your preferences. It doesn't care whether your models are elegant. It doesn't care whether your parameter fits look beautiful. It keeps ticking, and the residuals keep accumulating. And if a gravitational wave background exists, it will keep imprinting its signature with indifference that feels almost personal. That is why the hum is so powerful. It is not a story you can wish away. It is a pattern the universe repeats until you admit it. Maybe, in the end, the hum will resolve into a skyline, individual binaries you can isolate, localize, connect to galaxies, and study as living systems. If that happens, it will rewrite our understanding of how supermassive black holes grow, how nuclei evolve, how recoil and displacement shape galactic histories. Or maybe it will remain fog-like, smooth and stubborn, and begin to look more like a primordial relic. If that happens, it will force particle physics and cosmology to meet in the middle and negotiate new laws, new fields, new components, new early universe chapters we have not yet written. Either outcome is a win for reality, because the true enemy in science is not being wrong. The true enemy is being untestable. The hum is testable. It will harden or fade as more data arrives. It will show anisotropy or refuse it. It will reveal non-Gaussian lumps or remain smooth. It will allow continuous wave sources to emerge or deny you that prize. It will let the universe choose, through evidence, which story is closer to true. And that is the final point, the only point that matters. We do not get to decide what the universe is. We only get to listen well enough that it cannot lie to us anymore. The James Webb Space Telescope showed us the early universe is stranger than we expected. It pushed against our models with images that looked like contradictions. The Pulsar Timing Arrays are doing something similar, but quieter and deeper. They are telling us that spacetime itself is not a static stage. It is a medium that carries history in vibrations, a record of mergers or a record of creation. The hum is not the end of cosmology. It is the beginning of a new one, a cosmology that does not rely on one sense, a cosmology that can hear, a cosmology that can cross-check, a cosmology that will eventually force our models to either expand or break. And if they break, that's not failure. That is the universe doing what it always does, teaching us that our certainty was never the point. The point was the pursuit. If you made it this far, you're not watching for noise. You're listening for what's real. Subscribe to Nocturnal Space and leave a comment. I hear it. So I know you're here. And so the next chapter finds you.